Traveling to the future is already possible. But what about the past? It sounds like science fiction. DeLorean cars, paradoxes, alternate timelines, history rewritten. But here is the astonishing truth. According to modern physics, traveling into the future is not speculation. It is not fantasy. It is a confirmed consequence of the laws that govern our universe. The real mystery is not whether we can go forward in time. It is whether we can ever go back. Time feels constant. It feels universal. Seconds tick the same for everyone, everywhere. But in 1905, Albert Einstein shattered that assumption. In his theory of special relativity, he demonstrated something profoundly unsettling. Time is not absolute. It stretches, it bends. It flows differently depending on motion and gravity. And if time is flexible, then perhaps it is navigable. Before we go any further, if you're fascinated by questions like this, where physics meets the limits of imagination, make sure to subscribe and become part of our community. Here, we explore the ideas that challenge reality itself. Join us as we push beyond the known. Let's begin with what we already know: time dilation. Imagine boarding a spacecraft capable of traveling at 99.9% the speed of light. According to special relativity, as your velocity increases, time for you slows down relative to observers at rest. From your perspective inside the ship, everything feels normal. Your heart beats at its usual rhythm. Your clock ticks normally. But to someone watching from Earth, your clock runs slower. The faster you move, the more dramatic the effect becomes. At extreme speeds, a few years aboard the ship could correspond to decades, even centuries, passing on Earth. This is not hypothetical. Time dilation has been measured experimentally. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. Astronauts aboard the International Space Station age microscopically less than we do on Earth. The effect is tiny at everyday speeds, but it is real. If you traveled fast enough, you could leap into Earth's future. You would return to find civilizations transformed, generations passed, perhaps even humanity evolved. In this sense, time travel to the future is already physically possible, and gravity deepens the story. Einstein's general relativity tells us that massive objects warp space-time itself. Gravity is not a force pulling objects together. It is the curvature of space-time caused by mass and energy. The stronger the gravitational field, the slower time passes. Near a black hole, this effect becomes extreme. If you hovered close to the event horizon of a supermassive black hole without falling in, time for you would slow dramatically compared to distant observers. Hours for you could equal years for someone far away. This is gravitational time dilation. So again, the future is accessible, not easily, not practically, but physically. But what about the past? That is where physics becomes far stranger. One theoretical possibility lies in wormholes. A wormhole is a hypothetical tunnel connecting two separate regions of spacetime. Imagine folding a sheet of paper so that two distant points touch and piercing a hole straight through. Instead of traveling across the surface, you pass directly between them. In Einstein's equations, such structures are mathematically allowed. They are called Einstein-Rosen bridges. However, there is a problem. Wormholes would naturally collapse almost instantly. To keep them open, they would require something called exotic matter, matter with negative energy density. Negative energy is not pure fantasy. Quantum physics allows tiny fluctuations that can produce negative energy under certain conditions, such as in the Casimir effect. But whether enough exotic matter could exist to stabilize a traversable wormhole remains unknown. If it could, an even stranger possibility emerges. Suppose one end of a wormhole is accelerated to near light speed and then brought back. Due to time dilation, that end would age more slowly than the other. If the two ends remain connected, stepping through the wormhole could mean exiting at a different time than when you entered. In theory, this creates a time machine, but theory is not reality. Another route to the past appears in solutions to Einstein's equations, known as closed time-like curves. A closed time-like curve is a path through spacetime that loops back on itself. If you followed such a path, you could, in principle, arrive at your own past. Certain rotating black hole solutions, like the Kerr metric, contain regions where spacetime is twisted so severely that such loops may form. There are also speculative constructs, like the Tipler cylinder, an infinitely long, rapidly rotating cylinder that could theoretically drag spacetime around with it. But infinite cylinders do not exist. And rotating black holes, while real, likely do not allow safe passage into earlier times. Even if such structures exist mathematically, nature may forbid their physical realization. And then we confront the deepest obstacle of all, paradoxes. Imagine traveling back in time and preventing your grandparents from meeting. This is the famous grandfather paradox. If you succeed, you would never be born. But if you were never born, who traveled back to interfere? Or consider the bootstrap paradox. A scientist receives blueprints for a time machine from her future self. She builds it and later travels back to give the blueprints to her younger self. The information has no origin. It exists in a causal loop. Where did it come from? These paradoxes challenge the logical consistency of backward time travel. Some physicists propose the Novikov self-consistency principle. According to this idea, events along closed time-like curves must be self-consistent. You could travel to the past, but you would only perform actions that were already part of history. You cannot change the past because your presence was always included in it. In this view, free will bends to consistency. Another possibility emerges from quantum mechanics, the many worlds interpretation. If traveling to the past creates a new branch of reality, then paradoxes dissolve. You do not alter your own timeline. You create or enter another. But this shifts the question. Are we traveling through time or between universes? Stephen Hawking once proposed the chronology protection conjecture, the idea that the laws of physics prevent time travel to the past, preserving causality. Quantum effects, he suggested, might destroy any time machine before it could function. So where does that leave us? Forward time travel is experimentally verified. Backward time travel is mathematically conceivable, but physically achievable? That remains unknown. Modern physics has not unified general relativity and quantum mechanics. We lack a complete theory of quantum gravity, and without it, we do not fully understand spacetime at extreme conditions. It is possible that a deeper theory will reveal time travel to the past as fundamentally impossible. Or it may reveal that causality itself is more flexible than we ever imagined. Time, as we perceive it, flows in one direction. This arrow of time is tied to entropy, the second law of thermodynamics. Disorder increases. Eggs break. Stars burn out. The universe expands. Reversing time would mean reversing entropy on a cosmic scale. That may be the ultimate barrier. But here is the most profound realization of all. Time is not a universal river carrying us forward. It is woven into the fabric of reality itself, intertwined with space, shaped by mass, altered by motion. And if space-time can bend, stretch, and curve, who is to say it cannot loop? Perhaps time travel to the past is forever beyond our reach. Or perhaps it requires energies and technologies so far beyond us that they appear impossible today, much like flight once did to ancient civilizations. The real question is not whether time travel fits comfortably within our intuition. It is whether the universe permits it. And so far, the universe has surprised us before. Traveling to the future is not fiction. It is physics. Traveling to the past remains uncertain. But uncertainty is where discovery begins. If you've made it this far, you're already thinking beyond the present moment. So like this video, subscribe, and join us as we continue exploring the boundaries of what reality allows. Because at Next Frontier Science, we don't just ask what is possible. We ask what the universe is hiding. And sometimes, the future arrives sooner than we expect.